Gases. So gases are, I guess, usually elements or small molecules. Now, of these elements, they're all nonmetals. So you have hydrogen, nitrogen, oxygen, fluorine, chlorine, and then all of the noble gases. Additionally, small molecules can be gases. For example, hydrogen fluoride, carbon dioxide, methane. Now, you also can have butane as a gas. You see, this is a fairly small molecule. However, once we get into having larger molecules like hexane, those are no longer gases at room temperature. Because as you have increasing size of molecules, you have increasing dispersion forces. A greater attraction between the particles makes it so that they need a higher temperature in order to boil. So hexane actually is a liquid at room temperature, although it does give off a significant amount of vapor. That is that individual particles of hexane can vaporize. That is, though they're normally a liquid or a liquid at room temperature, they can become gas, and that gas is called vapor. Okay, so talking about pressure. Now, you might have learned in physics that pressure is just a force over area. Now, above you is actually 10,000 kilograms of air above a 1 meter squared cross-section around you. Now, this area right by you has above it for several miles 10,000 kilograms of mass, and it's got an acceleration towards you of 9.8 meters per second squared, aka gravity. So this mass times this acceleration is a certain force, 1 times 10 to the 5 newtons. Now divided by that 1 meter squared, you get this number of pascals. That is newtons per meter squared. Now this is actually at sea level 101.3 kilopascals. So you could say that pressure at sea level is really just the weight of all of the gas above you. And you can see that as you rise away or above sea level, you have a decreasing number of gas particles above you, and hence you have a decreasing weight of them above you, and hence a decreasing pressure on you from that gas. But there's another way of viewing pressure of gases, and that is just by interpreting the number of gas particles nearby, and also considering their kinetic energy. You see, at sea level, there's a high concentration of gas particles, and as you go higher and higher, there is a lower and lower concentration of gas particles. Now, gas particles, they're continually colliding with the walls of any container that holds them. In fact, we can define pressure as the pressure of these collisions. Yes, as they collide, they give some force to a wall, and the force over the area of that wall is pressure. And so if you have more gas particles colliding, you'll have more pressure. And if they have a greater kinetic energy, then they'll give a greater pressure as well. So this is really two ways of viewing pressure. Atmospheric pressure comes either from the weight of the gas particles above you or from the force of all these collisions. Now we can measure atmospheric pressure using a barometer. Now a barometer might involve just a glass tube filled with liquid mercury, and you can dip it upside down into a pool of mercury. Now initially, the pressure, or actually the force of gravity on all this liquid mercury will make it go downwards. Now this is opposed by the atmospheric pressure, which should actually make it go back up this tube. But initially, you might see that the force of gravity is greater than the force of air pressure, and hence the liquid mercury will fall. Until at some point, the force of gravity on this column of liquid mercury is equal to that pressure from the air. And so you can just know this pressure on the air, by knowing the force of gravity on this column of liquid mercury. Now this can be defined by the height of the mercury, and so you'll find that at sea level there is a height of 760 millimeters of mercury. Now we'll also call this 1 atmosphere. So this is atmospheric conditions at sea level here in JAXA. And the pressure is equal to the height in this case. But you can also describe pressure using a manometer. A manometer will measure the gas pressure within containers, typically in the lab. So if you're interested in the pressure of some gas inside your container, you'll use either a closed or open manometer. Now, if you have a closed manometer, you might have some gas particles colliding with that some liquid mercury here, forcing it downwards. Now, there's no gas on the other side of this. This is a vacuum, and so the only opposing force is the, I guess, gravity pulling this mercury downward. So you get to a point where the force of gravity is equal to the force of all these gas particles colliding. The force of gravity can be described by the height difference between these two levels, and so you can here, just like with the barometer, say that pressure is equal to the height. Now, in an open manometer, it's not exactly that way. So let's say that you have a bunch of gas particles colliding with the inside of your manometer. But in an open manometer, you also have gas particles from the atmosphere colliding with and giving pressure to that mercury. Now, in an open manometer, if you have the same height on both sides, it's only because the pressure of the gas inside your manometer is equal to the external pressure, the atmospheric pressure. So in this case, where height is the same, pressure is equal to the atmospheric pressure. But we can see that actually pressure is not just equal to that, it's equal to the atmospheric pressure plus height, but in this case, of course, it's 0. In another case where perhaps there is a height difference, this can only be because the pressure of the internal gas is greater than the pressure of the external gas. And so we can go back and say that the pressure is equal to the atmospheric pressure plus the height difference. Now, again, generally we're going to be referring to the height of mercury. We can actually define pressure as the height of mercury, although in some cases you might use the height of water. Now, 760 millimeters of mercury, which is also going to be known as 760 torr, this is equal to 1 atmosphere, which is also equal to 101.3 kilopascals. So sometimes you'll need to convert between units of pressure, for example, from 380 millimeters of mercury to a certain number of kilopascals. So you can use the equalities here. 760 millimeters of mercury is equal to 101.3 kilopascals. So you can build this unit conversion factor from that. And so you can go ahead and calculate that you should get about 51 kilopascals of pressure if you have 300 millimeters of mercury. All right, that's all. Thanks for watching.